In a previous video, we saw how to use fit-LM to perform a linear regression on some data, so to find the best linear function approximating some data. In this video, we're going to see how to use another function called polyfit to find the best polynomial approximation to some data. So let's start out by generating the data. Okay, I'm going to do this in a script, and let's have the data come from an actual polynomial, and I'm going to define that polynomial f using a pure function. Let's do x cubed minus 3x squared plus 1. And for our data points, let's use 5 data points, and let's have them be equally spaced between -3 and +4 using 5 data points. And for the y values, I just want to plug in those x values to f. And what's wrong with this? Well, I'm going to be plugging in this length 5 vector to this polynomial f, and that's going to give me an error if I don't tell MATLAB to use element-wise operations. So let's do that by adding these periods before the caret symbols. And let's just look at what this data looks like. And rather than joining the data points using straight lines, let's have them be unjoined and marked with these little circles. So let's save this. Let's call it polydata. And let's run the script. Okay, so here you can see the function, or here you can see the data points corresponding to the function f. And maybe you can agree this looks like it's coming from a cubic polynomial. So that's going to be our data. And then we want to use the idea of polynomial regression, which it's interesting mathematically. Polynomial regression isn't any more difficult than linear regression. It's like a multivariable version of linear regression. But we're not going to worry about the underlying mathematics behind linear regression or polynomial regression. We're just going to care about what is the MATLAB function that does these two types of regression for us. And so the function for polynomial regression is called polyfit, and it takes as input the x coordinates of the data, the y coordinates of the data, and then the upper bound of what degree terms do you want in your polynomial. So my polynomial comes from degree 3, and let's restrict ourselves to degree 2 and below. And let's see, let me comment out this plot for a second, and let's just run this script and see what it looks like. So I've saved it, and let's run it again. And so what is this telling me? Well, notice that I didn't have a semicolon on this line, so this is printing the result of polyfit. And you're supposed to read this as telling me what are the coefficients of the degree 2 polynomial produced by polyfit, and you need to read them with the leading coefficient coming first. So this is the x squared coefficient, this is the x coefficient, and this is the constant term. Okay, the x to the 0 coefficient. And let's name this. Let's name it p for that polynomial. So I've saved it. Let's run it again. And so now notice that this p has shown up in the workspace. So I can try to evaluate that polynomial. For example, I can try to evaluate it at 2. But notice that p, what was that? That was just this length 3 row vector, -1.5, 9.66, -4. And so when I do p parentheses 2, that's just giving me the second entry in the polynomial. So that's not how you evaluate the polynomial at 2. Here's how you evaluate it at 2. So polyval stands for polynomial evaluation. Then the first input is the polynomial, the vector of the coefficients. And the second input is where do I want to evaluate it. So maybe it'll be easier if I evaluate it at 0. And if you evaluate any polynomial at 0, then you get the constant term. Okay, just like I get here. So now let's go back to this plot. And in addition to plotting the data, let's also plot how does the polynomial look. Okay, so I'm plotting the same x-coordinates and the output of this degree 2 polynomial estimation for the data. So I've saved it. So not a very good approximation, and the reason for that is because I was restricting myself to degree 2, whereas our polynomial came from degree 3. What happens if I allow myself degree 3? Okay, now it fits perfectly. Maybe I don't like how it's choppy like this. Maybe I'd rather it look more like an actual polynomial. How can I do that? Well, here's one way. Let's name x1, and let's use a bunch more data points. And it's not very good coding to be typing the same thing twice. It would be better for me to name -3 as a variable and then use that variable name. But I know that in this video, I'm not going to change the x-min or the x-max. So that's why I'm okay just typing it twice to save a little time. So now for the polynomial portion of the plot, it's going to use 100 sample points rather than just 5 sample points, and it's going to look a lot smoother. So I've saved it. Let's run it again. Okay, so now that looks perfectly smooth, and it still fits the data perfectly. And what if I don't want it to fit the data so nicely? Well, rather than having the data come exactly from a polynomial, let's perturb the data a little bit. So let's go for I from 1 to the length of y. Okay, and I'm just going to go through each entry in y, and I'm going to add some random number to it. So we'll do yi equals yi plus. So if I just did rand or rand1, this would give me a uniformly chosen random real number between 0 and 1. If I multiply it by 10, that gives me a uniformly chosen real number between 0 and 10. And if I want it to be symmetric, so like sometimes it's positive, sometimes it's negative, then let's subtract 5 from this. So let's save it. And now I expect that there is no polynomial, no degree 3 polynomial that's going to perfectly fit this data. Let's see. So I've saved it. Let's run polydata again. So there you can see it doesn't go perfectly through these data points, but it still matches pretty well. What if I allow myself a higher degree polynomial for my approximation? Like what if I use degree 10 rather than degree 3? So the true source of this data is coming from some like slightly randomized version of this degree 3 polynomial. So in some ways I should expect the outcome to be worse when I use this degree 10. And in a sense it will be, in a sense it won't be. Let's see. So I don't know if you agree, but I would say this is looking worse, even if it goes perfectly through the different data points. And the plot is looking kind of strange, but that's because to match this degree 10 polynomial, MATLAB has zoomed out a lot. So now, even though my data points do not go much below like -40, the polynomial graph goes all the way down to like -450. And what's happening here is what's known as overfitting. So this polynomial that we've produced, this degree 10 polynomial, is overfitting the data. Like, let me use some more data points to try to make this more clear. Let me use 9 data points between -3 and 4. So I've saved it. Let's run it again. So this is looking really unnatural, and this is what's known as overfitting the data.